So in the video I'm replying to, I was talking about Wieferich primes, and Wieferich primes are these amazing primes that have a connection to both Fermat's little theorem and Fermat's last theorem. Let me explain why. So a prime number is called Wieferich if 2 to the p minus 1 minus 1 is divisible by p squared. Let's see first what's the connection with Fermat's little theorem. So Fermat's little theorem implies that if p is a prime bigger than 2, then 2 to the p minus 1 is always congruent to 1 modulo p. And that implies that p is always a divisor of 2 to the p minus 1 minus 1. In other words, 2 to the p minus 1 divided by p is an integer, not just a rational number. And the question is this integer divisible by p also? That's not implied by Fermat's little theorem, but if this integer is a multiple of p, then p is called a Wieferich prime. Now, Wieferich primes seem to be very rare, and we actually expect them to be that rare, and we have found only 2 Wieferich primes so far. The only 2 primes that are known to be Wieferich are 1093 and 3511. So why are we interested in Wieferich primes? We are interested in them because Wieferich was trying to prove Fermat's last theorem, and in 1909 he came up with the following criterion to prove Fermat. So if p is a prime and x, y, z are integers that satisfy Fermat's last theorem, and p does not divide any of x, y, and z, this is actually what's called the first case of Fermat's last theorem, then p is a Wieferich prime. So if we knew that there are no Wieferich primes other than the 2 that I showed before, then we would be able to prove Fermat's last theorem, at least the first case of Fermat's last theorem, completely. However, unfortunately, we do think there are infinitely many Wieferich primes. They're just very, very rare, and they're hard to find, but we think there are infinitely many. So at most, this proves Fermat's last theorem, or the first case of Fermat's last theorem, for very many, many primes, but not for all the prime numbers.